In this video, I'll be showing you how to do electron configuration diagrams. This is going to be a very simple method of approaching drawing electron configuration. So let's assume we have some kind of ion. Well, actually, let's start with an atom. So let's say we have germanium. And we want to know the electron configuration of germanium. So first we want to find out the atomic number, which will give us the number of protons and hence the number of electrons, since the atom is going to be electrically neutral. So we're going to look at this dynamic periodic table, and we're going to find germanium, which happens to be 32. So we can say that the atomic number is 32. And since it's neutral, it's going to have 32 electrons as well. So then we want to draw the orbitals starting from the 1s sublevel. So we basically have 1s, 2s, the 2p, the 3s, 3p, the 4s, and then the 3d. And then we're going to have the 4p. So if you don't want to memorize this, there's another way of finding a general kind of rule of thumb to approaching this. So you can draw out 1s, 2s, 3s, 4s, 5s, 6s. That's probably all you'll need, maybe up to the 5s. And you have 2p, 3p, 4p, 5p, and then you have the 3d, 4d, 5d. Based on the scope of this course, you probably only need up to maybe this area at most. So then you have the 4f, and then the 5f. So you can just draw arrows going this way, and this is the order in which these sublevels, or these orbitals, are going to be filled. So as you can see, we have the 1s, and then the 2s, the 2p, 3s, 3p, 4s, and then the 3d, 4p, 5s, and then the 4d. So for this particular electron configuration diagram, we only need up to the 4p. So we're going to be covering all of this area. So what we do is we have to follow a few principles. So one principle is basically just building in an upwards direction, and that's known as the Aufbau Principle. It's sort of a simplification of it, but it basically means we're building upwards. In German, it literally means to build up. So the Aufbau Principle basically says we start from the lower orbitals and then we move upwards. Then we have to follow another principle in which we have Pauli's exclusion principle. Pauli's exclusion, and it's basically just saying that we're going to have a maximum of 2 electrons per orbital. So let's say we have an orbital, let's just say it's the 1s, for example. So we have a maximum of 2 electrons, and it's also stating that these electrons have opposite spins, so they're not spinning in the same direction. And we're going to indicate the spin of an electron by the direction of half an arrow. So it's going to be something like this and this, each one representing an electron, and the arrow, the direction in which the arrow is pointing, represents the direction of spin. And Pauli's exclusion principle is basically saying that each orbital, each one of these little lines here indicating an orbital, has a maximum of 2 electrons, so each one can hold only 2 electrons, and they have opposite spins. And then another rule that we have to follow is known as Hund's rule. So basically, let's say we have a sublevel that has multiple orbitals, let's say the 3D sublevel. So this one has 5 positions. Each one can hold 2, so it can hold 10 electrons in total. So what Hund's rule is basically saying is, it's basically saying that when let's say we have 8 electrons that we have to fill, that we have to put into the 3D sublevel. So we can fill it out in many ways. We can say, let's do this, 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 and we're leaving an orbital that's empty. So Hund's rule is basically saying that it's kind of like an analogy that can be used is like it's an empty bus, and people don't want to sit next to each other unless they have to. So what it's saying is that if an electron doesn't have to pair up, it'll find its own kind of space for itself. So let's say we have 8 electrons. So we have the first one here. The second one, it doesn't want to pair up with the first electron, so it'll sit here, 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 and then that's 5. Except after 5, there's no orbitals that have 0 electrons already in them, so they have to begin to pair up. So typically we just start from the left and work to the right, but it doesn't. But the order isn't very important. So we have 5, 6, 7, 8. So this is following. This basically demonstrates Pauli's exclusion principle with the opposite spins and the maximum of 2 electrons, and it also demonstrates Hund's rule. So combining all 3 of these rules, 1, 2, 3, we're able to draw an electron configuration. So we have the atomic number is 32, so we have 32 electrons to put in. And what I'm doing here is I'm not actually counting them, because there is something interesting to remember. If you have the 1s, 2s, 2p, 3s, 3p, up to 4s, this is going to be exactly 20 electrons. And the 3d is easy to remember because it's 10 electrons. So after this we'll have 30 electrons. And then we have a 4p subshell to fill. We're going to apply Hund's rule, or the empty bus rule, and we have 2 electrons left. So we have 1, 2. Then we can draw out the overall kind of the full electron configuration. So we have the 1s2, 2s2, 2p6, 3s2, 3p6, and after calcium, the 3D sublevel actually falls beneath, in terms of energy, the 4s sublevel. So we're going to write the 3d10 before the 4s2. And then we have the 4, 2. And this is going to be the full electron configuration. In a later video, I'll be showing you how to do sort of a partial or noble gas configuration, in which we simplify parts of this by using a noble gas. In this case, we'd be using argon, and then we'd be building on top of that. It's sort of simplifying the full electron configuration. It's sort of an abbreviated form, and I'll be discussing that in a later video.